Hey there, it's Shannon Myers, and today we will be looking at properties of determinants. So there's some very cool applications, including Cramer's rule and using determinants to find area, volume, and equations of lines and planes. So let's do it. Example 1, we're going to sort of discover our properties here. So we need to find all these determinants, and this is sort of really kind of a math stretching exercise or warm up, if you will. So go ahead, pause the movie, find these determinants by hand, and then check with me and see how you did. Good luck. Alrighty, let's see how it went. Okay, now that we did all these determinants separately, why don't we just check out some potential properties, right? So we got the determinant of A is 10 and the determinant of B is -7. So here, if we were to think about this, the determinant of A plus the determinant of B would equal to 3, correct? Whereas the determinant of quantity A plus B, those two determinants added first, was equal to 49. So these two are not equal. Cool? But if we look at the products, what's going to go on? Well, the determinant of A times the determinant of B would be what? 10 times -7, which is -70. And the determinant of the product of those two matrices was also -70. So it looks like perhaps these two might be equal. So let's check it out. It turns out that the determinant of a matrix product, as long as A and B are square matrices of that same order n, the determinant of the product of the two matrices is equivalent to the product of the determinants. Cool? Okay, so now let's check out this situation here. All right, so for this matrix A, what's our determinant? The determinant of A is equal to 10 plus 3, which is 13, correct? And 3A, the determinant of 3A is going to equal to the determinant of 3, -3, 9, and 30, which in turn is going to be what? 90 plus 27, which is 117. Cool so far? Okay, well, let's see how this sort of relates to the determinant of A. So we know that the determinant of A is 13, right? And we know that the determinant of quantity 3 times A is going to be 117. So, I mean, if I factored 117, I know that 3 divides it, and remaining would be what? 39. And then dividing out of 3 again, we would get 13, and then 13 and 1. So that's the prime factorization. So, looks like the determinant of 3 times A is equal, of course, to 117, which is equal to 3 squared times 13, which is 3 squared times the determinant of A. Cool so far? So what would our supposition be about the determinant of B? Or sorry, the determinant of quantity 3 times B. We know that the determinant of B is equal to -7 because that's from example 1. We already did this. And then now why don't we go ahead and find the determinant of 3 times B. So that's going to be the determinant of 6, -3, 12, 0, 3, 9, 9, -6, 3. Good so far? I just tripled each of the elements in B, or entries in B. So if I expand about, I'll just do the middle row there. And this would be minus, plus, minus. What's going to happen? We're going to get 0 plus 3 times 6, 12, 9, 3 minus 9 times 6, -3, 9, -6. And we'll have 3 times 18 minus 108 minus 9 times -36 plus 27. And that will end up being -270 plus 81, which gives us a result of -189. Okay, so let's go ahead and factor that one and see what it looks like. So I'll just do the positive portion of it. So 189, 3 divides this, and it goes in 63 times. And then 3 divides 63, we get 21 remaining. And another 3, and we get 7 remaining, and then a 7. So here we go. It turns out that the determinant of 3b was equal to -189, which is equal to 3 cubed times -7. I'll put the negative there. But what is that? That's equal to 3 cubed times the determinant of B, So note that B has dimension 3 by 3, A has dimension 2 by 2. And do you see how in the first one we squared our scalar? And in the second one we cubed our scalar. So it turns out that if A is a square matrix of order n and C is a scalar, then the determinant of quantity C times A is C to the n times the determinant of A. Groovy? Okay, so let's look at this proof. Why don't we let A equal to an n by n matrix. So we'll have A11, A12, all the way down to A 1n, and then we'll have A 2 1 all the way down to A n 1 because A is n by n. And then the diagonals will go all the way until we get to A n n. And then we'll go across here until we get to A 2n, and then we'll go down. And then we'll go, here will be what, A n 2, and then dot, dot, dot. Good so far? All right. C times A would then be CA 1 1, CA 1 2, all the way down to CA 1 n. And then we'd have CA 2 1, CA 2 2, all the way across to CA 2 n. The first column would keep going all the way down to CA n 1. The second column would keep going until we got to CA n 2. And then we'd keep going over and then down from the last column until we got to CA n n. And then the diagonal also goes across. Groovy? All right. So we'll let A, ij belong to the real numbers for 1 less than or equal to I less than or equal to n, and 1 less than or equal to j less than or equal to n. And then we'll also let C belong to the real numbers as well. Okay, we've got it all set up now. So what do we know? We know that the determinant of A is equal to the summation from j equals 1 to n of A. I'm going to just do this expansion about the first row, all right? A1j, C1j, where C is the cofactor, all right, of the corresponding entry. All right, so now the determinant of CA then would be, well, we'd have the summation from j equals 1 to n of C times what? Good. A 1 j, all right? Good. So what will happen is the C that's attached to our cofactor is going to be n minus 1, because remember that you don't include the entry that you're on. So when you're looking for the cofactor for entry A1j, you're going to delete that entry, aren't you? A1j. And so you have n minus 1 C's being multiplied together. Groovy? Okay. So, and then that will go with the cofactor C1j. Okay, well, what's this equal to? That would be the summation from j equals 1 to n of CA11 times C to the n minus 1 times the cofactor for the entry in the first row, first column, plus CA12 times C to the n minus 1 times the cofactor corresponding to entry A12, so C1, 2, and you'd keep going on in that way until you got to CA1n, and then the scalar C would be raised to the n minus 1 times our cofactor 1n. Cool so far? Each time, in each term rather, aren't we multiplying C to the 1 times C to the n minus 1? Exactly. So each of these are going to be simplified to C to the n, because 1 plus n minus 1 is just n, times A 1j times our cofactor 1j. All right, well, what can we do with a scalar from a summation? We can bring it out, correct? So we would get C to the n times the summation from j equals 1 to n of A1j C1j. But what is that? That is equal to C to the n times the beautiful determinant of A. We're all done. Cool, cool? Now we're looking at determinants and inverses. Fun times. Just for the practice, I know you can enter these in on your calculator, but it's good to know how to do it by hand. So I'm going to go ahead and do these by hand, and then you can, go ahead and do it on your own and then check your work. All right? Here we go. The determinant of A is going to be equal to negative 12 plus 12, which is 0. Well, let's see. We've got this 0 determinant, and so what's going to happen with the inverse, you think? Well, I don't know. Let's check it out. That might be interesting, right? So let's check it out. So A inverse, to find that, what would we do? We want to do A and then I2, because we have a 2 by 2. And that's going to equal to negative 3, 6, 1, 0, negative 2, 4, 0, 1. So I had joined the identity matrix to the matrix A. And I need to do my row operations. So let's see what we have. If I do negative 2 row 1 plus 3 row 2 for a new row 2, let's see what happens. So our first row isn't going to change. Our second row is going to be what? Well, we'll have 6 minus 6 is 0. That would be negative 12 plus 12 is 0. And then we would have what? Negative 2 and 3. What do you think about that? I mean, there's no way we're going to be able to get the identity matrix on the left side, correct? It's impossible. So that's okay. What does that mean for us? It means that A inverse does not exist. And what does that tell us about A? What was that term? So A is singular. Cool, cool? So yeah, we found the determinant of A, but we can't find the determinant of A inverse. Cool, cool? All right, let's see what we have. And remember that connection in your mind, okay? Determinant of A was 0, and A is singular. There's a connection there. All right, so next up, let's take a look at B. Well, the determinant of B is equal to 35 minus 22, and that's going to give us 13. Perfect. All right. Now, how do we find B inverse? Remember that one shortcut way? It would be 1 over the determinant of B, and then what do we do with that matrix? Beautiful. We swapped the main diagonal entries, and we put opposite signs on the other entries. So B inverse will be 1 over 13, 7, negative 2, negative 11, and 5. So B inverse will be 7 thirteenths, negative 2 thirteenths, negative 11 thirteenths, and 5 thirteenths. Groovy? All right, so let's check this out. What is the determinant of B inverse? Well, that's going to be 7 thirteenths times 5 thirteenths minus negative 2 thirteenths times negative 11 thirteenths. Cool, cool? All right, so that's going to give us what? 35 over 169 minus a minus a minus, so we'll have minus 22 over 169, which is 13 over 169. But what is that? That is 1 over 13. How does that relate to the determinant of B? Well, it seems to me that the determinant of B inverse, which is equal to 1/13, seems to be 1 over the determinant of B, right? Cool, cool. Okay, so let's see if that's a thing, and it is. Theorem 3.7, determinant of an invertible matrix. A square matrix A is invertible, non-singular, if and only if the determinant of A is not equal to 0. Very, very important concept. Okay? So, here we go. Let's kind of test out our theory here. Actually, we've sort of already discovered this. The determinant of an inverse matrix is actually, if A is an n by n invertible matrix, then the determinant of A inverse equals 1 over the determinant of A. And that's what we found in the other one. So let's go ahead and do the proof of that one. Let's check it out. So what do you think we should do? What is in the premise? Beautiful. The premise is that A is an n by n invertible matrix. So let's use the fact that since A is invertible, there has to exist an inverse, right? Some A inverse such that A times A inverse equals the identity matrix IN, which is equal to A inverse times A. That's by definition. What do we also know? Well, we also know that the determinant of A is non-zero since it has an inverse, right? And that one is by Theorem 3.8. Okay, so no, 3.7, sorry, 3.8 is what we're trying to prove. All right, so now what do we have? The determinant of, so now the determinant of A times A inverse by one of our properties there is equal to the determinant of A times the determinant of A inverse, correct? What else do we know? I mean, we also know that the determinant of A times A inverse has to also equal to the determinant of the identity matrix from here. So that's where we get that one. So, okay. What is the determinant of the identity matrix? Beautiful. Remember, that one is 1. So, what do we have? The determinant of A times the determinant of A inverse has to equal to 1. Now, we know that the determinant of A is non-zero. So, if we isolate, and this is just a scalar, so we can isolate the determinant of A inverse, and it would be equal to 1 over the determinant of A. Cool, cool? Okay, so now coming back, let's just use the property to find example 4 since we worked it out in part B of example 3. So the determinant of A is equal to negative 3 plus 6, which is 3. And so the determinant of A inverse would be equal to 1 over the determinant of A, which is 1/3. Cool, cool? All right, very good. Now, equivalent conditions for a non-singular matrix. These are very important to know. So if A is an n by n matrix, then the following statements are equivalent. So if one is true, they're all true. A is invertible. A times x, the vector x equal to the vector b, has a unique solution for every n by 1 column matrix. A times the matrix x equal to the 0 matrix, it has only the trivial solution. And then A is row equivalent to what? These are all ones we had before. Beautiful. To IN. A can be written as the product of, awesome, elementary matrices. Now we're adding another one here. The determinant of A is non-zero. So remember how when we were doing those spanning problems, and it was like such a difficult process because there were unknowns for the constant matrix, the constant column vector. So now all you have to do is evaluate the determinant, and if it's non-zero, you know that there's a unique solution, and so that thus it would span. So put that in your toolbox. We'll be using it again. All right. For example 5, we want to determine if this system has a unique solution. So using our newfound knowledge, what do you think we should do? Beautiful. We can find the determinant of the coefficient matrix. Okay, so our result was negative 10. And so this is the conclusion we're going to draw from finding this determinant. The determinant of this coefficient matrix A is equal to negative 10, and which is non-zero. So therefore, by all of those equivalent, statements, what does that mean? There exists a unique solution to this system. And furthermore, if one wanted to, if you were, checking to see if a set spanned, you would thus be able to say, therefore, blah, blah, blah spans whatever space you're in. And so this is a very, very useful tool. Okay? All right, so next up, let's take a look at finding the determinant of A and the determinant of A transpose. So the determinant of A is equal to negative 14 minus 24, which is negative 38. And A transpose will be 7, 2 going across, and then 12, negative 2 going across. So the determinant of A transpose equals negative 14 minus 24, which is negative 38. So look at that. So these two are the same. Groovy? So that brings us to Theorem 3.9. If A is a square matrix, then determinant of A transpose is equal to the determinant of A. Example 7. Solve the system of linear equations. And we're assuming that the determinant of the coefficient matrix is non-zero. That's what this is saying. All right? All right, well, let's check it out. If we want to solve this system, what do you think we need to do? Well, we could form the augmented matrix, couldn't we, that corresponds? And so here, this would be A11, A12, B1, and then A21, A22, B2. Cool so far? Very good. Now, we want to be able to get our, 0 in the second row, first column. And just like normal, we want to get a 0 in the second row, first column. So let's do it. If I multiply the top row by negative A21 times row 1, and then I add to that A11 times row 2, what's going to happen? Well, row 1 will remain unchanged, and my new row 2 will be, well, this will zero out as planned, and then the second one, what are we going to have? We'll have negative A12, actually we're going to need more space here. Okay, so one more time. We'll have negative A12, A21 plus A11, A22, right? So I'm actually going to flip that around so it's prettier, and that'll be A11 times A22 minus A12, A21. All right, now what about for that last one? let's see. So we'd have negative A21B1 plus A11B2. So I'll do it like that, A11B2, just to make it prettier, minus A21B1. Good so far? Very good. Okay. So, what do you think we should do now? Well, we've got reduced echelon form, right? I mean, we could go ahead and zero out where the A12 is, but it might just be easier to work with it from here. So let's see what we've got. Putting this back in terms of a system, we would have A11x1 plus A12x2 equals B1. And then, all right, so the second one will have what? We'll have quantity A11 times A22 minus A12 A21 times x2 will equal to A11 B2 minus A21 B1. Good so far? So, isolating x2, we will have A11 B2 minus A21 B1. That's going to be over. Let's look at this quantity. So if A is equal to this coefficient matrix, A11, A12, A21, A22, what's the determinant of A? Beautiful. A11, A22 minus A12, A21, right? Well, isn't that what we have on this left side here? So here we're really dividing by the determinant of the coefficient matrix. So here, these are equivalent. All right? And that'll make it look a little prettier. So that's what we have for x2. Now, for x1, we can work with this equation here and then substitute what we got for x2 into that one. So we'd have A11 times x1 plus A12 times x2. And x2 is going to be A11B2 minus A21B1 over the determinant of the coefficient matrix. And that's all going to equal to B1. We want to isolate the x1 terms, right? So let's see what we end up with, okay? A11 times x1 is going to equal to B1 minus, and now I'm going to distribute the A12 through the quantity, and we'll have A12 times A11 times B2 minus A12 times A21 times B1 all over the determinant of A. Cool so far? Okay. So next up, well, we can isolate our x1, can't we? So x1 will end up being 1 over A11 times. Now I'm going to get a common denominator and simplify a little bit on what we had initially. So to get a common denominator on this stuff, I would need to multiply by the determinant of A over the determinant of A, right? So I will have the determinant of A times B1 minus A12, A11, B2 plus, distributing the minus, A12, A21, B1 all over the determinant of A. Groovy? All right. So continuing, we will have x1 equals. Now it looks like I'm going to have to turn one of the determinant of A's into, into the other way to write it. So here we will have A11 times A22 minus A12 times A21 times B1. I'm going to put the other B1 next to it, so we'll have plus A12 times A21 B1 minus A12 times A11 times B2. That's going to be all over A11 times the determinant of A. Good so far? Awesome. So then x1 will be A11 times A22 B1 minus A12 times A21 B1 plus A12 times A21 B1 minus A12 times A11 B2 all over A11 times the determinant of A. So just to give you a heads up, I replaced this determinant of A with this here expression here. All right, don't you just love the algebra? Now, do you see that these two terms are going to zero out, right? So we will have A11 times A22 times B1 minus A12 times A11 B2 over A11 times the determinant of A. If I factor out an A11 in the numerator, I will have A22 times B1 minus A12 times B2. And that's going to be over A11 times the determinant of A. And so now the A11s are going to divide out. And look what we have. We end up with x1 is equal to A22 times B1 minus A12 times B2 all over the determinant of A. Interesting. What if we were to turn the numerator into a determinant? I mean, what would that look like? Well, let's see. If I'm working kind of backwards, it could look something like this. Couldn't it look like, let's see, it'd have to be B1, A22. That gives me my first term there. And then, so that's the main diagonal. And then I'd have what? A12 and then B2. How cool is that? And then over the determinant of A. So you know what? Let's check out what we got for x2. So this one, couldn't I write this one as A11 and then B2 down the main diagonal, and then the other diagonal I'd have A21 in the second row first column and then B1 in the first row second column over the determinant of A. So this determinant is equivalent to this expression, and this determinant down here is equivalent to this numerator. Cool, cool. So this is Cramer's rule for 2 by 2s. And they call these matrices that you get in the numerator, they have a subscript on them. So when you replace the first column with the constants and the second column stays the same as the coefficient matrix, that ends up being the determinant of A1 over the determinant of A. This x2 that we had found ends up being the determinant of, so now the second column was replaced with the constants, and so the subscript shows A2 over the determinant of A. Isn't that pretty cool? So you can go directly to the solution using determinants as long as the determinant of the coefficient matrix is not 0. And so just to rewrite, we get x1 was equal to the determinant of A1 over the determinant of A, and x2 was equal to the determinant of A2 over the determinant of A, where A was equal to our coefficient matrix, A1 is equal to our coefficient matrix except for the first column is replaced with the column of constants. So B1, B2, and then this will still be A12, A22, and then what would A2 be? Beautiful. You would have A11, A21 for our first column, and then B1, B2 for the second. Groovy? Again, this is why Cramer's rule works for a 2 by 2 matrix which has a non-zero determinant. And I know that was a lot of algebra and stuff, and I know I'm a math nerd. And you might think that's why I did all that, which was part of the reason. But I also did that so you could, remember the formula. If you see where it comes from, it's easier to remember. If a system of n linear equations and n variables has a coefficient matrix A with a non-zero determinant A, then the solution of the system is. So we would get x1 is equal to the determinant of that A1 matrix over the determinant of A. x2 is determinant of A2 over determinant of A. And then it keeps going until you get to your last variable xn. And what do you think the xn will be? Beautiful. The determinant of A sub n over determinant of A, where the jth column of A sub j is the column of constants in the system of equations. Okay? All right, so let's check these examples out. If possible, use Cramer's rule to solve the system. So what we want to do here is immediately find the determinant of the coefficient matrix. Don't make the mistake of finding all the other determinants. If the determinant of the coefficient matrix is 0, you cannot use Cramer's rule. All right? So A equals -1, -2, 2, and 4. And so the determinant of A will be -4 plus 4, which is 0. So Cramer's rule does not apply. Cool, cool? All right, next up, let's check this one out. Our A will be -8, 7, -10, 12, 3, -5, 15, -9, 2, and the determinant of A, actually for this one, let's go use some of the technology, all right? All right, so the determinant of A is 1,149, which is non-zero. So we can go ahead and find the other stuff. Well, what is the other stuff? A1 is going to be, so your subscript is 1, so in column 1, you put the column of constants. So that'd be negative 151, 86, and 187. And then the other ones will stay the same. 7, 3, negative 9 for column 2. And column 3 would be negative 10, negative 5, and 2. A2 will be negative 8, 12, 15 for column 1. Now we'll put those constants in column 2. So negative 151, 86, and 187. Then we'll still have negative 10, negative 5, and 2 for column 3. And A3 will be negative 8, 12, and 15 for column 1, column 2, 7, 3, and negative 9. And then column 3 will have the column of constants. Groovy? And so we need to find these determinants. So let's check out our technology. One nice thing about using Octave is that it's easy to copy and paste, even using the iPad, amazingly. Cool so far? All right, so x1 will be equal to 11,490 divided by 1149, which is equal to what? 10. Very good. X2 will be equal to negative 3,447 over 1149, which happens to be equal to negative 3. And then X3 will be 5,745 divided by 1149, which happens to be equal to 5. Groovy? So our solution is the ordered triple 10, negative 3, 5, and it's a consistent system. Good, good? All right, so now we get to some cool applications, very visual ones. So the area of a triangle in the xy plane, if it's got vertices x1, y1, x2, y2, and x3, y3, ends up being, you've got a plus or minus, and of course, since it's area, you would choose whatever makes the positive result. So plus or minus 1/2 times the determinant of, so you have your ordered pairs, and then you need to have a column of ones, and that enables you to manipulate them. We'll see what happens for this particular one in a moment. Okay? Let's check it out. Let's check out a picture of this. Okay? So let's suppose that we have, I don't know, some triangle. So suppose this is x3, x2, x1. And let's say we have a triangle, I don't know, that looks something like this. So point here maybe, point here. I'm trying my best not to make it look square. We don't want that. Or like it's a right triangle. We do not want that. So if I, kind of take a look at this triangle, the triangle of interest, would look something like this, which is not a right triangle, correct? And then our ordered pairs, of course, this is x1, y1. This would be x2, y2. And this point would be x3, y3. Good so far? Very awesome. So now, let's do it. Let's show you why this works. Recall that the area for a trapezoid is equal to the average of the bases, okay? This is how I like to do it. Average of the bases, base 1 and base 2, so that's an average, and then times the height, okay? So if we think about that, we can make a series of trapezoids and add and subtract the areas to find the area of this triangle, all right? So remember, this is the region of interest that we want the area for. So we're going to pretty much mess this up and then simplify it to show you why the area formula is what it is. Okay, so here we go. If we have our first trapezoid, so the area for trapezoid 1, okay? And let's see, why don't we make trapezoid 1 be here and here and then here and here. Good so far? So that's the first trapezoid. And notice that it contains, in its area, it will contain area that's not in our triangle. All right, so this length here is going to be y1 minus 0, right? Which is y1. What about this length right here? Awesome. That's going to be y2 minus 0, which is y2. Good so far? So if we take the average, and you see those are the bases because they're the edges that are parallel to each other, okay? So we've got y1 plus y2 over 2, and then the height is actually going to be our change in x, all right? And so this measure here is going to be x2 minus x1. Are we good there? All right. So that'll be times x2 minus x1. And then our next trapezoid, let's check it out, will be, well, can't we make one using that same edge? Okay, so now let's make a different trapezoid. So area of trapezoid 2. So, well, why don't we take care of this trapezoid? It shares that line that made up one of the parallel bases, and then it's over here, okay? So this length, of course, will be y3 minus 0, which is y3. We already had the other one as y2, and so the height of the trapezoid will be x3 minus x2. So here we go. We'll have y2 plus y3 over 2 for the average of the bases, and then x3 minus x2 for the height of the trapezoid. And then lastly, so notice that that's gotten more than the area we need, correct? So if I go ahead and take a look at this trapezoid here, so we'll share that base that's made up of, you know, that we found from plotting the point x1, y1 and drawing the line down to the x-axis. We'll go across this part of the triangle now, and then we'll come down here and then here. Cool, cool. So the area for trapezoid 3 is going to be what? Beautiful. It's going to be y1 plus y3 over 2, and then times, awesome, x3 minus x1, because it's this whole line that travels from x1 to x2 is the height. Okay? So, all right, let's check it out now. Little bit of algebra. So we basically are going to need to add these two, and then from that we're going to be subtracting this one, okay? Because this was what was too much, right? That third one, that was too much area. So we're minusing that out. Now, let's see what it looks like, okay? All right, pretty cool, huh? So that is why the formula works. And then just so you can sort of match things up in case you didn't quite catch it, this quantity here is equivalent to this determinant here. And this quantity matches up with this determinant. And this third quantity matches up with this determinant. And then the three together, along with the ones they were expanded about, makes the 3 by 3 determinant. All right. So next up, let's go ahead and use this. Find the area of the triangle whose vertices are the following. So why don't you go ahead and pause the movie and try working this out yourself, and then start it up again and check how you did. Good luck. All right, let's see how you did. We'll have the area will be plus or minus a half. And by the way, that's where this plus or minus comes in. It's gonna depend on if the determinant is positive or negative. So plus or minus 1/2 times the determinant of. So 1, -1, 1. 3, -5, 1. And 0, -2, 1. So our area will be equal to plus or minus 1/2 times. So I'll go ahead and expand about those ones. So it'll be a plus minus plus. And we'll have 1 times 3, -5, 0, -2, minus 1 times 1, -1, 0, -2, plus 1 times 1, -1, 3, -5. And so our area will be equal to plus or minus 1/2 times. -6 minus 0 is -6. And then we'll have minus -2 minus 0. So minus a -2 is plus 2. And then let's see, plus 1 times -5 plus 3 would be plus -2. Good so far? So that's going to give us the area is equal to plus or minus, these 2's will zero out, so plus or minus -3, which of course we would have the area is 3 square units. Cool, cool? All right, so the next groovy formula here, test for collinear points in the xy plane. So 3 points, x1, y1, x2, y2, and x3, y3 are collinear if and only if the determinant of that same matrix that we've been using so if the determinant of this matrix is equal to 0, then the 3 points are collinear. All right? Okay. So the 2-point form of the equation of a line. So again, these are different ways of finding these things you probably already know how to do. You need to know how to use determinants to find them for the exam. Now for this one, instead of having 3 ordered pairs that we know, we're going to let one of the ordered pairs vary. So we'll just call it x and y so that we get the equation of a line. So what you do is you set the determinant of x, y, 1, and then x1, y1, 1, x2, y2, 1. So you set this determinant equal to 0, and you'll get the equation of a line. Now, volume of a tetrahedron, our volume will be equal to plus or minus 1/6 now, and this is times the determinant of x1, y1, z1, and what do you think? Beautiful, 1. x2, y2, z2, 1. x3, y3, z3, 1. And x4, y4, z4, and 1. Cool so far? Very good. All right, so let's find the volume of the tetrahedron with vertices 1, 1, 1, 0, 0, 0, 2, 1, -1, and -1, 1, 2. All right, so here we go. Our volume will be plus or minus 1/6 times 1, 1, 1, 1, 0, 0, 0, 1, 2, 1, -1, 1, and -1, 1, 2, 1. So that will give us our volume equal to plus or minus 1/6 times. And what do you think we ought to expand about? Very good. This might be a good one down here. And let's see, that would be plus, minus, plus, minus, plus. So here we go. We'll end up with 0, minus 0, plus 0, minus 0, plus 1 times the 3 by 3, which is 1, 1, 1, 2, 1, -1, and -1, 1, 2. So our volume will be plus or minus 1/6 times, I'll just expand about this first row now, and so the signs will be plus, minus, plus. So we'll have 1 times the determinant of 1, -1, 1, 2, minus 1 times the determinant of 2, -1, -1, 2, and then plus 1 times the determinant 2, 1, -1, 1. Cool, cool? So our volume will be plus or minus 1/6 times, that'll be 2 plus 1 is 3, And then minus 4 minus 1 is 3. So we'll have a minus 3. And then plus 1 times 2 plus 1 is 3. So that gives us a volume of, we'll choose the positive on that. Oh, sorry, this one should have been 1/6. It was a transcription error. Okay. So here we'll end up with our volume is equal to 3/6, which is 1/2, and that's of a cubic unit. All right. So next up, there's a test for coplanar points in space. So these are kind of similar to the other ones. If the determinant that you used for, the tetrahedron volume is 0, or the determinant part of it, not the one plus or minus 1/6 part, then what you'll find is that the points are coplanar. So the determinant of, x1, y1, z1, 1, x2, y2, z2, 1, x3, y3, z3, 1, and x4, y4, z4, 1. So if this determinant is equal to 0, then the 4 points are coplanar. All right. Now, here's kind of a cool way to find the equation of the 3-point form of the equation of a line. So an equation of the plane passing through the distinct points x1, y1, z1, x2, y2, z2, and x3, y3, z3 is given by, again, we let one of the ordered triples, we're going to let vary. So the determinant of x, y, z, 1, and then we'll have x1, y1, z1, 1, x2, y2, z2, 1, and then x3, y3, z3, and 1. And then you set that equal to 0 and solve it, and you'll get the equation of a plane. Groovy? All right, so that wraps it up for today. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. If you like what I'm doing, please subscribe. Thank you. Bye-bye.